One of the advantages with Lagrangian mechanics that we have stated repeatedly is that we can ignore the forces of constraint. This is usually a good idea because it will simplify the problem solving, but sometimes you really do need to know what the forces of constraint are. For instance, if you want to build a building, you need to know what the internal forces are that keep the building in place, so that they can be properly dimensioned, then the building doesn't fall down. In that case, the methods that we have developed so far are actually not going to be good enough, and we have to come up with an alternative. To do this, I have to introduce a little bit of mathematics here, known as Lagrange multipliers. They aren't specific at all to Lagrangian mechanics or the calculus of variations, so I'm going to start by explaining how they work in the context of regular optimization theory, the way you've been taught it previously. So let's consider some function of two variables, f of x and y, and it reaches an optimum, a maximum or a minimum, when the gradient of f is 0. That's something that we have, that you should be familiar with. We talked about that already. So what we have here are the contour lines of f. So basically we have here that f of x and y equals some constant. That's how these lines are chosen. And we know that the gradient is going to be perpendicular to these lines. So we have in particular that here is the gradient of f. You are all well aware of this. And if we don't have any constraints on f, then the optimum is clearly here. This is the point where the gradient is equal to 0. This is the unconstrained optimum. So if we now add a constraint to this, which would be something like g, some function g of x and y has to be equal to some constant a, then this no longer applies. We are no longer able to use set the gradient to equal to 0 and find the optimum, simply because the maximum or minimum point here may not actually be consistent with this constraint. So one way to solve this, to get around this, would be to just use this to come up with a relationship that will express y in terms of x, for instance. Then f will be a function of just x. Right, and then we can find the optimum just by setting f prime of x equals to 0. And this is equivalent to what we've done so far in Lagrangian mechanics when we've taken into account the constraints. We've used the constraints to reduce the number of generalized coordinates, and then we've gone on our merry way. But there is a different way to do that, and that is the method of Lagrange multipliers. So to explain how this works, let me now show you this curve here. Right? This curve, the constraint curve, this equation here defines a curve that we can put on here. So let's do that. It will look something like this. Right? Here, this corresponds to g of x and y equal to a. All these other curves here are constant contour curves for other values of this constant here, but this is the particular constraint that we are interested in. And as you can see, it doesn't go through the maximum here, and that's why we can't use the gradient of f equals 0, because that's only true there. Here the gradient, this is the optimum point clearly, on this particular constraint line, but the gradient is not equal to 0 there. So if we don't want to use this method, this particular method for finding the optimum in the presence of a constraint, we have to use the Lagrange multiplier method. So if you look carefully now, at this point here, this is the optimum. You can see that if you follow this curve along, let's say this is a maximum, then the value of f in blue increases until we get to this point, and then it decreases again. So this is where the optimum is. Now if I were to draw the gradient to g at this point, it needs to be perpendicular to the constant contour lines. So it will be in this direction. Here is the gradient of g. We can do the same thing for the gradient of f at this point. That's the gradient of f right there. And at the optimum point, what happens is that the contour lines for the g function, for the constraint function, are going to be tangent to the contour lines for the function that we are trying to optimize. So just from this geometric constraint, we can see that we can write that the gradient of f is proportional to the gradient of g. Right? That's really what we see here. We can write one vector as a multiple of another vector, and the constant proportionality here, in this particular case, turns out to be negative. This constant of proportionality is known as the Lagrange multiplier. Now, of course, this is not the only point where the two gradients are parallel to one another, or where the contour lines are tangential to each other. We can sort of draw some sort of, see on this line here, the gradient of f equals lambda times the gradient of g. So all of these points on this green line here satisfy this condition, but in order to find the particular one that we're interested in, we use this constraint to find lambda. Okay. So in other words, we would use this constraint here to find the lambda that corresponds to this particular point. And this is the method of Lagrange multipliers for optimizing a function in the presence of a constraint without reducing the number of variables. So let's see how this works in a specific example. Let's say that we want to find the extremal potential energies of a pendulum. Right, so we have, in a pendulum, we have the gravitational potential energy. That's mgy, where y is the vertical position. Now, this function doesn't have any extrema. It decreases when y decreases, it increases when y increases, but it has no maximum or minimum. So if you were to plot it, all we get is if you were to plot the contour lines of this function, all we get are a bunch of horizontal lines. Right? And there's no place where the gradient of u is 0. The gradient of u is different from 0 everywhere. It's mg, y hat. But you also have a constraint. The constraint is that we're looking at a mass at the end of a pendulum, right? So, right, this is kind of what it looks like. This is our pendulum. So the constraint would be that x squared plus y squared, square root of this is L, right? The length of the pendulum if the origin is there. So what we need to do now is say that, okay, this is what we call g of x and y. And this is the function that we need to optimize in blue there. So if you were to plot these, what you get is this. Right? We have u equals mgy. Constant potential lines are horizontal, just like what we said. And then we have that the length here from the origin to this point is L. Right? We can see, of course, relatively easy, but just looking at this problem, is that the extremum of the potential energy is either when the pendulum is at its bottom position or at its top position. So geometrically, it's very clear what the answer has to be. But now we want to use the method of Lagrange multipliers to prove this mathematically. So let's see now. We have, this is our f function, this is our g function. I'm going to call this f of x and y. So we need to have the gradient of f has to equal to lambda times the gradient of g. Okay, if we'll take the gradient of f, it's going to be 0 in the x direction and mg in the y direction. And then this has to now equal to lambda times the gradient of g. And if we calculate that, we find that this is equal to 1 over the square root of x squared plus y squared, and then times the vector x, y. And this has to be true, and it also has to be, we also have to choose lambda such that this constraint is valid for this particular length of the pendulum. So just looking at this, we can see immediately, looking at the first line here, that what we get is x equals 0. Then we get some other expression here for y, but we can then just apply the constraint, which gives us that y equals plus minus L. Just like what we said, right? We have x equals 0 and y equals minus L or plus L. Those are the places where the potential is at its maximum and minimum values. And if we plug things in, we can also see here that, if y equals L and the square root of x squared over the square root of x squared plus y squared, this is always equal to L, then this gives us that lambda equals mg. So mg is actually the force that the particle experiences, the bob of the pendulum experiences as it hangs from this point. So in the next video, we're going to apply this method now to Lagrangian mechanics. We will find then a Lagrange multiplier as well, with a caveat now that it's no longer going to be just a constant, it will actually be a function of time. But other than that, everything will work exactly the same way.